All right, hello and welcome back to our Emerging Science of Anaerobic Digestion webinar for our November 1. A couple things. If you have questions at any time during the presentation, please feel free to put your questions in the chat. I get to be your speaker today as well as your moderator, so I promise that I will do a reasonable job on my time management as we go. And then a couple things. So our speaker next time will be Robert Burns, and he's going to talk about ways to get manure out of deep pit swine barns and the impact that storage time has on anaerobic digestion efficiency or biogas potential. So I'm really looking forward to that one. But today, I am going to be presenting, and we're diving back into sort of the basics. So we're going to talk about biochemical methane potentials, BMPs. If you see that word and work on water qualities, you might think best management practices. But today we're going to talk about what it means for biochemical methane potential, why you use it. We're going to talk about toxicity and the assay that people use for that, the anaerobic toxicity assay. And then we're going to talk a little bit about bench scale testing. And the objective for today is really to talk through how do the tests work? How do we think about and use the data that we get from them? And when should we use them? What questions are we trying to answer? How do they help us think about how to design or operate a digester with hopefully a little bit more science behind it? So just to get started, quick review of what we're happening. We're thinking about what substrates do we have. The world I work in, I tend to think of manure and ag residues, and that comes with lots of stuff, pathogens, micronutrients, and most importantly, unstable organic material, right? So that carbon material that we're trying to convert. No matter what material you're thinking about it in generally the same terms. It has some organic material in it, that thing that we're trying to use or mine efficiently from it, and then it comes with some other stuff or baggage. And that baggage might be, hey, I got something that has a lot of salt in it, or this thing has a lot of selenium in it, or man, I can get this slaughterhouse waste, but they throw a lot of cleaner in there. And we want to think about what that impact that has on how efficiently a digester will run and sort of how the process works, right? So generally what we're doing is we're taking this organic material, we interact it with a consortium of microorganisms. I think we're starting to have some ideas about what organisms we want, maybe how to cultivate the microorganisms that are in the digester, but that's still relatively new science. And what we can say is that those microorganisms are generally trying to process carbon from large complex molecules and reduce them down into the simplest forms they can get them in, which tends to be methane, carbon dioxide, hydrogen sulfide, and ammonia. And then we're left with a lot of material in the treated effluent, and that tends to be relatively low pathogen. I'm going to call it nutrient rich, or at least it tends to have most of the nutrients that we started with, probably 99.9%, as long as we're not settling it in the digester. We do lose a little of the volatile nutrients, specifically nitrogen and sulfur to the gas, but it tends to be small amounts. And depending on how you scrub it, you can recover those. And then relatively lower odor, stable from at least a carbon perspective, liquid material. And we might do further post-processing like we've talked about in the past on that, but that's really all we're trying to do. So I wanted to start out with why we test. And when you think about biogas production or biogas work, there's some substrates that we've studied a lot. I think dairy cattle manure, we've seen a lot of people sort of run BMPs on it originally, work their way up to mini reactors, and a fair amount of implementation on full-scale farms these days. So you might not need to say, I want to go all the way back to a BMP or an ATA on that. There might be reasons to do it yet, but you might say, we have some pretty good experience in this area, pretty representative farms, and say I can jump ahead sort of on that spectrum. But sometimes we show up with something unique where we haven't seen digestion before. Uh, Maybe someone says, I have all this waste cardboard. How much gas can I make with it? What's it worth, right? And then you might want to start at the beginning. Or I envision a world where we're going to digest prairie and we don't have much information on how much gas you can make from prairie. Sometimes going back to that original test and working your way through sort of is the best approach we have. So I think every one of the tests that people generally use, so biochemical methane potentials, anaerobic toxicity assays, mini reactors, they're all trying to answer slightly different questions. And the place to generally start is with that biochemical methane potential. And it's really a test of how much methane can we make from this stuff, right? So it's a really basic question. And then you work your way up and say, Well, it comes with other things that I don't really want. Does that cause a problem? Or are there things that might get in my digester for a reason that cause a problem? And those are sort of really supposed to be quick diagnostic tools of, is this stuff worth studying more, right? And you might say, well, I can get sugary wastewater from Coca-Cola, right? And we know it's going to have a high gas potential because it's basically sugar water. And because it's sugar water, it doesn't tend to have things that are microbes can't tolerate to it. Maybe we don't need to do those two steps. Maybe we can say, yeah, but how do I manage it? Do I need to add nitrogen to it? And that's really where mini reactors in my mind come into play, right? We're going to try and see how stable is it, how well it works. And then, especially if you're doing something new or unique, like I have all this fibrous biomass material, corn stover, and I need to figure out how to get it into a digester, feed it through a digester. That's when we want to start thinking about pilot scale and really try to answer those material handling questions that we have. So just a little background on the digestion process. And the reason we're doing that is when you think about biochemical methane potential or anaerobic toxicity assays, we can sort of focus them on which step do we want. Now, with biochemical methane potential tests, it's really typically focused on that methanogenesis step as what we're measuring. But it doesn't have to be. You could think about doing it sort of, how do I measure hydrolysis? How do I measure acid production, right? So you can sort of break up the steps and say, where am I having an issue? Where are things working well in those tests? It isn't the standard way of doing it, but it is possible. So just recognizing that there are multiple steps in the process and how we think about it can sometimes be helpful in troubleshooting or thinking about what that data actually tells us, and then how we should respond in either managing or in the next thing of trying to make the process work better. Okay, so the biochemical methane test is really a batch test under ideal conditions. And we're going to add an inoculum, which is basically an anaerobic seed, a substrate, which is the material we want to see how much gas it can make, and then a nutrient broth, which is filled with some trace minerals and a lot of alkalinity. And the reason we're doing that, and as you think about it, is we're trying to create ideal conditions. So the nutrient broth, the alkalinity, we're trying to buffer and we're trying to hold the pH relatively constant. We're trying to give the microbes anything they could need and really see, can they break down that material? And as they break it down, what do they turn it into, and specifically how much methane it makes? So when you do this sort of test, you put all those things in a bottle, you flush the headspace with gas. I put a sealed septum on mine. There are some systems that don't work with a sealed septum. They're continuously measuring either pressure or letting the gas go into a different container and measuring how much gas they get. But that's really sort of what you're doing. And you let that go until completion, until you hit a maximum gas and aren't making any more. If you live in the United States, we tend to think about that as somewhere in the neighborhood of 20 to 40 days. If you live in some European countries, they might think about it as we want to run that for 100 days, right? And it's sort of what's your patience level and what level of true gas production are you getting. So when I run mine, typically 20 to 40 days, I'm trying to get all the gas I could get from the material. I make a little microbial biomass in there since it's anaerobic, not a lot. The reason the Europeans and the Germans have sometimes went longer is they break down the microbial bodies sort of as it dies off and get a second burst of gas production. And either one's right. I think it's sometimes helpful to know which one it is. And for the most part, those gas production numbers aren't that different, but that's sort of the methodology they're taking. And while the bottles I'm showing you there on my lab bench, I was doing something else. I was trying to see if I could make stuff foam. And you can see, voila, I did. It's the same sort of setup that I use for a BMP. It's just in that case, I put in something different than maybe that inoculum medium. So just a few things as you're doing this. People have found it helpful to characterize the test material. Certainly, when we put it in a bottle and incubate it, we're getting a total amount of methane we're making. But you'll often normalize that in some way, either against total solids or volatile solids or a carbon content measurement. A lot of people love to use chemical oxygen demand, which is COD. I've seen some people use soluble COD, and oftentimes we just want to measure P, sort of an indicator. In manure worlds or worlds where we have maybe chunky material that is hard to make homogeneous, oftentimes we've used volatile solids sort of as the normalizer because it's some measure of organic material. Some people believe that carbon content might be better. If you have something like sugary wastewater, COD tends to work relatively well. Uh, You could, in theory, use COD with manures. It just the measurements tend to be maybe a little bit more va variable than volatile solids or something that's maybe more consistent. And that's why we've tended to go away with that. From a theoretical standpoint, COD is often preferred because as you break down chemical oxygen demand, there's a thermodynamic equilibrium to how much methane you made. So those two should be in proportion. Volatile solids give some of that up, but it is much more consistent as you measure. So again, just to sort of give you some perspective on what you're doing here, there is a nutrient broth that they recommend you use. Uh, if you want the reference for that, it comes from Spies. He told us this is a typical nutrient broth that we should use. So he wrote a great book on anaerobic digestion, and that's what most people in the industry would use, buffering for alkalinity. You put in an inoculum source. And that obviously varies from lab to lab. I try and keep a completely mixed digester in my lab. I feed it Old Roy dog food that's ground up and a nutrient broth as I run it to try and be as consistent as possible. Some people would get their inoculum source from an operating anaerobic digester. There's no right or wrong answer on this, but the one thing I want to sort of caution or suggest is that that inoculum source hopefully doesn't make a difference in the result of the test and the total amount of biogas we make, but the inoculum source can sort of change how quickly digestion occurs, right? So if I have an inoculum source that's really rich in bacteria, active bacteria in it, it might speed my digestion up. If I have an inoculum source that's maybe a little less bacterial population, maybe that goes a little bit slower. As you think about how to load these, it depends on your test apparatus, but you're trying to make an appropriate amount of methane and biogas that you get a good measurement. For me, I'm using 250 milliliter serum bottles. I'm trying to make roughly somewhere between 150 and 200 milliliters of methane in my 30-day run, uh, just to get into a nice measurement range. If you were using a different measurement tool than I would, you could do something different, but that's essentially what you're trying to do. As you think about setting the tests up, it's important to always have replicates. These are relatively small biological reactors, and I think generally for homogeneous materials, we tend to get pretty good repeatability. If you have a material that's highly variable, you tend to get more variable biogas reduction just because it's harder to manage everything. And then the last thing I wanted to point out is that inoculum to test material ratio is something people sort of control because it has an impact on how quickly the digestion occurs. And what we generally think about is we want somewhere between the same amount of volatile solids from inoculum to test material to maybe two times the amount of test material to inoculum on a volatile solids basis. But it's really a bacteria source and it's controlling how quickly that digestion occurs. And one way to think about it is if you work with digesters before, we might think about that food to microbe ratio. And essentially, that's what we're manipulating here. The test material is the food. That inoculum is sort of my microbe ratio. And by trying to get a relatively low food to microbe ratio, you're trying to push the reaction to get done more quickly within some bounds. All right, just some pictures of sort of what I do in my lab. Again, there's many ways to do this. They do sell automated systems where you don't need to have students poking bottles with syringe, but the idea is sort of still the same. So there I have a completely mixed reactor, heated blankets around it, so we have it controlled at 35 degrees Celsius all the time. We bubble gas from it to an inverted tipping bucket so we can measure how consistent the gas production is just to make sure it's functioning well. It has an automated feed, some of the hoses you can see going in there. So it pumps every 3 times a day, so many milliliters of that dog food nutrient broth material in, keeps it in there for about 30 days and then pulls it out. On the side, you can see a spigot, and that's where I would pull my inoculum source out. From there, I'm putting all those materials into those septum bottles, and I put white rubber stoppers on top. They're self-healing. You can poke them somewhere in the neighborhood of 10 times before they're worthless. So you get about one biochemical methane test out of them, and then you're discarding them. So I use them once and get rid of them. Uh, if you don't know much about your material, I like to put zip ties around them to hold them down. If you can make a pretty good estimate of how much gas you're going to make, and know you're going to measure frequently enough, you don't have to do that and you still get a good seal. But when you guess wrong, it helps save some of the bottles for a little bit later time. I use a gas tight syringe that I poke through there. So I let that gas pressure inside move the barrel of the syringe up, and I can read from that graduated scale how many milliliters of biogas I made, and then I run it through an infrared methane analyzer, right? Because I'm trying to figure out how much methane I made. Again, there's sophisticated systems to do this now that are automated. When we first started running them, there weren't many of those on the market, but all those tests work. Oftentimes, they will accumulate biogas over the whole 30 days instead of maybe having it over a function of time in some of those systems, but it depends and can be run either way. One important part is to run it through some sort of methane analyzer at the end. You don't just want biogas production. So a question that you might think about as you're trying to use that test or what it could answer is, how does feed in ingredient formulation impact my manure biogas methane potential? So here I just have it normalized per milliliter of sample. It made the most sense for my case uh, for lots of reasons because I tended to generate the same amount of manure across all the diets, but the solids content varied based on some of the things I did to the diet. So I was just trying to normalize to the one that I thought made the most sense for me in this case. But just to orientate you here to what's happening, that first letter, either C, the last letter, sorry, is either a C or an F, and that tells me the grind size of the feed. So in this case, if it's a C, that means it was ground to 700 micron before I fed it to the pig. If it's F, it was ground to 350 microns before I fed it to the pig. And then those middle designators there and the first letter are sort of a diet designation. So C-SBM would be a corn soybean meal diet. C-DDGS would be a corn distillers grain diet. And then the last one would be a corn soy hull diet. So you can see we sort of replicated the same three diets at two different grind sizes. And it actually had a fairly big impact on how much methane potential you had per milliliter of manure. And maybe no surprise, if you grind the feed finer, I reduce the biochemical methane potential of that manure. Mostly because the pig does a better job of digesting the carbon in it the finer I ground it. That was more impactful on some ingredients, that soybean meal and the DDGS, than maybe it was for the soy hulls, at least statistically, right? But we saw that same trend for all of them. So that's sort of the question you might be trying to answer is, how does a feed ingredient impact my manures, BMP, or how does storage time before I get it to my digester impact the amount of methane I might generate? Or I have this new substrate I've never seen before, what might I expect for methane potential? So people have run a fair amount of BMPs on lots of different materials. I just wanted to give you sort of a summary of what people often show and what the results might look like. So there you can see a bunch of different manure types, the solids content that they got them at, the volatile solids content they got them at, the COD, a pH, and then in this case, they normalized that total cumulative methane production over the length of the test by how much volatile solids you started with. And you can see a decent variation, right? The variation there that they're reporting is so that first beef manure, one bottle to the next varied by 3%. On the second one, the outdoor pen, where you might be getting more dirt in some samples than other samples, essentially, there was more variation, right? So manures that can be more similar, liquid beef manure, you can tend to get less variation. Some of the other ones, more variation. But they give you a general feel. And as people have done this for some of the substrates, I think we get sort of this is typical of the industry. And if you are feeding something relatively standard, it's a good number for you. Noting that everyone formulates rations a little bit differently. Their animals have different performances. Our manure management system, collection, storage, handling tends to be a little different, and it can change those numbers. So sometimes it's worth investigating a little further. If you look at that and say, hey, your swine slurry is only 131, what's wrong with swine slurry there? I've looked at digesters and I've looked at the carbon intensity score calculator that California puts out, and they say it's closer to 450 milliliters of methane per gram of volatile solids. Absolutely. That sample comes from a deep pit where that manure had been stored for a longer period of time. To me, deep pits tend to average 150 if I just go get them. Fresh manure tends to be closer to 350 from my experience of measuring them. So I think that's one reason to still do a BMP, is that handling system, what you put your manure through makes some difference. When you start thinking about what people get for data, they're actually doing something like this generally. On that x-axis, I'm showing incubation length and the number of days that we've had the bottle going there. And then on the y-axis, I've accumulated methane production. This time, again, still normalized in terms of VS. And what's typical is you'll see some lag phase that lasts somewhere between 3 and 7 days, depending on the material. You really ramp up, and hopefully by day 20, you're getting close to that maximum biogas production. And then it sort of stables off. And when you say you had two readings that are pretty much the same, that can be a sign that you've went long enough and can stop. The other thing I wanted to point out is from bottle to bottle, you'll notice that as I'm going through that ramping phase, I tend to have higher standard deviations or higher variation from bottle to bottle. And as I get towards the top, those sort of come back together. And that's just a sign that the lag phase in those bottles were slightly different. And maybe a good reason to say that kinetics from these experiments aren't always super useful for designing a digester, but they can be semi-helpful for telling you something about a substrate. Just as importantly, I wanted to tell you a couple things that that type of test doesn't tell you. Uh, so if you're making CO2 and say, I want to measure CO2 and how much CO2 I can get, those systems are heavily buffered. They have alkalinity in them, and that really influences the carbonate system and how much CO2 I end up with. And then for H2S, they can tell you a little, but the amount of H2S you get off in your digester has more to do with mixing intensity. And my relative mixing intensity in my models might be different than yours. I see I have a couple questions floating around, so I was going to try and look at them. Yes, we will make sure that we have a reference for the textbook in and the nutrient broth shared on our SciBox. And then I do have a question on mono and co-digestion from manure from different species, and we'll try and hit that one at the end. So that's a great question too. But we'll make sure we get the nutrient broth up there, and we'll share specifically the recipe from the Species book. There are other recipes that work. It's just a nice one as a starting point to point you in the right direction. Okay, so next I wanted to move on to an anaerobic toxicity assay. And I really think of this test as a caution light. And you're really asking, is there something in this material that my digester doesn't like or can't handle? And the test in itself is really a question of how does the rate of anaerobic digestion compare when I add this potential toxicant to it to compare to what it would be when I just add a defined substrate. Oftentimes I'll use sugar as my defined substrate. And there's lots of potential toxicants that we could think about. Some of the ones that you might run into might be salts or metals. Ammonia is one that people see and talk about. I think ammonia is an interesting one because a lot of work shows that maybe you can overcome ammonia toxicity. One that I tend to deal with is feed additives. Some famous ones might be rumensin or Andersen. We feed cattle or pigs some of those to hopefully reduce enteric fermentation during their digestion. And then you have questions like, how long does that carry over in the manure? And is it going to affect my ability to use this in an anaerobic digester? And then I think there's been a lot of great work on detergents. A couple to think about might be if you're running a dairy or a beef barn and have digesters, what are they doing with their copper sulfate foot baths, right? And that can sometimes cause an issue. Or what happens with milk house wastewater or cleaning water from a swine farm? And if I would slug load that into my digester all at once, do I have an issue? So I wanted to show you what we're doing here. It's really set up similar to a BMP. We want to characterize a lot of the same stuff, but while I'm showing you, I put almost the same stuff in the bottle, it changes a little, right? So in this case, we want to test material. So it's whatever our potential inhibitor is, which is oftentimes our substrate as well. Not our substrate for this test, but a substrate for a digester. You still add that inoculum. We tend to add more inoculum in this case because I'm going to add another food source. You can use lots of different things. You want a standardized food source that you use. I tend to use sugar because we know how much stuff it's going to make. And again, we're going to flush out that headspace and then measure biogas production. So it's set up similar, except I'm adding an extra food substrate to it to sort of mediate it. And I'm not adding that nutrient broth like we did before because we want to potentially have some of the struggles that you might see in a real world situation. Now that can have a downside since I haven't buffered it. Sometimes if your ATA says this stuff didn't work very well, you'll want to check why, and we'll try and talk a little bit about that troubleshooting and what it might tell you. This is just an example of what I did with the substrate. And in this case, I was using Andersen, so a swine feed additive, and I ran this a really long time. Most of the time with anaerobic toxicity assays, we target 7 days. The reason that I ran it for an extended period of time is there's a lot of evidence that says it breaks down during manure storage or manure treatment. And I wanted to see when it sort of breaks down and when it overcomes that toxicity. So normally we won't do that, but sometimes it can be helpful. But essentially what I've plotted there is just methane production as a function of how long I incubated it. And you can sort of see the trend as a function of time. They're all making methane. And maybe the ones I hit harder with Narrison at the beginning made less methane, and then they start to catch up. What people generally are trying to do that is calculate an inhibition or what percentage of that methane I'd made, right? So I kept going on my test until all of them weren't statistically different. Uh, but essentially you can see that by adding that toxicant to it, we had reduced methane, right? And you can see what percentage of the control we were. Now, what people often plot or what species reference or the method tells you to plot looks more like this. So on the x-axis, people are going to plot sort of that concentration that they added. So you need to make sure that you're using a concentration gradient uh, that covers sort of the span. And on that y-axis, I'm going to calculate percent inhibition, which is basically 100 minus whatever the percent of methane I had made, right? So if I've made 60% of the methane of the control, I'm going to have smaller inhibition than if I'd made 20% of the inhibition. And you're really looking at the slope of that line. So steep slopes tell you that that stuff is really, as your concentration increases, much more toxic to the anaerobic conditions. And I think what I took away from this is basically with time, my slopes got shallower and shallower and shallower, so almost flat, and I overcame the toxicity. And the method and what people tell you about this test is it really is sort of a nice, yes, you might have some issues, but you can overcome a lot of the toxicity that you might see initially in some cases by microbial community adaptation. So I'm measuring how toxic it is to the inoculum I put in, not to a bacteria that might adapt to that condition. And that's why sometimes the tests have to be thought about carefully, right, in the context of what they're doing. Just because you see it's toxic doesn't mean you can't overcome it. And you might be able to say, I still want to go up to a pilot scale digester to see sort of can we overcome that toxicity and have a more stable digestion, even though there are some signs that it might be toxic when I just slug load it. I think oftentimes you want to know why did that happen? So that's what I'm trying to illustrate here. I still have that narrow dose on the x-axis, and then I measured how different the microbial community essentially was from stuff I didn't treat to stuff I did. And the more Narrison I put in, the more different I made the microbial community, right? So essentially it says that the microbial community shifted a lot because I put that in, and that slowed gas production. So a good sign that it was inhibitory to whatever I started with as a community, and I caused some big changes. It doesn't necessarily say you can't overcome it again, but it points to what's happening there. So I think one of the challenges I see a lot in ATA is the material you want to evaluate is both the substrate and the potential toxicant. And that means as you're doing this, you're changing the substrate or the amount of carbon that you have and the stressor at the same time. And essentially that sometimes means if I put in just a little bit of that, I might have 10% more COD and I end up making more gas, even though it's still somewhat toxic to it, right? Now, that generally tells me it's not toxic enough that it's a problem, but it does just make you have to think a little bit more about what the data is telling you as you look at and see it. The other thing I want to definitely point out is that if you do have things that fail, where they make very little gas, you should be trying to diagnose why. And a few things I like to do on that is check for pH, check for VFA accumulation. Uh, we have run some of these, especially with a substrate like glycerin, where it breaks down really fast. And since it's not a highly buffered system, I didn't throw that alkalinity in. Sometimes what you're doing is rather than seeing something that's toxic, you're souring your digester. You're making VFAs more rapidly than your microbial community could process them into methane. And I wouldn't necessarily call that a toxicant. It's just somewhere where you have to think about how am I going to manage this digester to make sure that those stay in balance. Again, you can also do this ATA sort of for different steps, right? I normally am looking at the last step, that methane production. Methanogens tend to be the most sensitive, but that may or may not always be the case. All right, and then the next one I want to just point out is when to run a mini digester, and you're trying to simulate real world digester performance with at least relatively continuous loading. And what we're typically trying to answer in that case is, will the system sort of be stable over a long term? Or what happens if I do something to it? Like what happens if all of a sudden we dump our hoof baths and have a whole bunch of formaldehyde slug loaded into our digester, or copper sulfate slug loaded into our digester? Or what happens if someone calls me tomorrow and says, can you take this bioprocessing waste product this one time and I slug load it into my digester? They're much better at answering those types of questions, especially if you have sort of that BMP and that ATA to guide how you might take them in. So just some examples of some digesters we have run before in my lab. Lots of people do this. The scales can vary. Uh, in this case, we were trying to make things about 60 liters. It looks a little different than that completely mixed digester. These are plug flows. So the near one, you're on the feed side. You open that tube up, pour your substrate in, and then hope that gravity helps pull it out the other end. The further one away in the picture, you're looking at the outlet side, has a valve on it, so we could open it up and try and drain the right amount of stuff out. These were relatively thick materials, plug flow, so if you're wondering why that T is there on the near one with that port, well, every now and then we did get a plug and you had to plunge and push to get stuff to flow in. They tend to work relatively well. Uh, if you're doing thinner materials and can use pumps, love it. It automates it. If you're not, well, grad students are nice and undergrads are nice to try and feed them. But the scale sort of is dependent on the question you might want to ask or answer and the materials that you're sort of dealing with. So just some example of data from here, and this comes from a friend of mine, Steve Sell, when he was doing his graduate degree, he ran a whole bunch of biomethane potentials on materials. Sort of he did it actually 6 times throughout a year and came up with his maximum BMP of that mixture and his minimum. So he evaluated something like 6 to 8 different substrates and sort of weighted averaged what they might be to put in. And then he ran 3 different digesters as a function of time, saying, how did the amount of methane I make stay within the bounds? And when you sort of, the question we got earlier, I think, about co-substrates and mixing is sort of relevant to this. So for each of those substrates, a BMP can sort of give you an estimate of how much gas you'd make. Oftentimes we'll run them independently. No need to mix them together and run a BMP on that. Just use math and average weight them. Each one of those you could run an anaerobic toxicity assay too to say, is this substrate a potential challenge? Is it not? I don't know that you always have to do that. I think it's dependent on sort of the manure you're working with or the material you're working with. But then oftentimes if you want to see how stable that is or how they work together, that's really a mini digester sort of question. And the reason I say that is you could be thinking they're synergistic. I'm trying to adjust my C to N ratio by mixing a high carbon manure with liquid swine manure to increase gas production. Maybe that helps break down that more recalcitrant or high carbon manure more quickly because I have nitrogen available to me. Or maybe it was a question of if I ran this thing alone, it didn't have enough nitrogen in it actually, right, to get good efficient digestion. So mixing them and running them with a digester helps for some stability and look at a lot of those properties. Um, Co-digestion, I think, is really a great thing. You're really sort of constrained by solids content when you think about your mixtures and some other things, but that gives you a tool to think about how thick can I make it, where do I am I sort of optimizing it, and how easy is management. So the graph I'm showing you here, he has hydraulic retention times on that x-axis. Normally, people are going to try and run something like 2 to 3 hydraulic retention times before they start collecting reactor data. The startup is interesting. It can be neat, but it's not really indicative of long-term performance. So you have to run some backgrounding to get it set up, basically stabilized, and then you're looking at it once it's stabilized, what's happening. And I really think of them as a troubleshooting scenario. What happens if I do this? So what happens if I get a truckload of X today and feed it all today versus I bleed it in? Do I get a foaming issue? Do I have a toxicity issue? What's sort of recovery like after I slug load something like that? They're much better for that type of question than those lab scale tests. If it's, hey, I have this stuff, I'm thinking about a digester, is it feasible? BMPs are a much better starting point. This is when you've sort of decided, yeah, the project is looking like I might be able to make this work, but I don't want to invest $1 to $3 million in the system quite yet. Let's see if we can make it run consistently over time and figure out the management challenges we might have from the things we're actually digesting. And then the last one is really moving up to that pilot scale, right? And they're sort of bridging the gap between biochemistry, sort of what we're doing in the lab, and really the engineering aspects of the project. So I think they're super exciting, but to me, they're mostly working out material handling ideas and challenges, how to heat it, pump it. Are we going to have solids accumulation in the digester if we don't mix it? So they're answering a different type of question. And you could say, well, I can do some of those like solids accumulation from some simple lab tests. And you're right, you can, right? So if you just do a settling test, you might be able to see how quickly does it settle? How completely does it settle? How concerned should I be with that? But running it into digester especially at scale, sort of handles or helps address some of those issues. And I think oftentimes when I run some of my larger mini digesters where I have students feeding and managing every day, they start to get to sort of semi-pilot scale, but I refuse to call them pilot scale because when you have a person hand feeding, it's different than being able to automate with a pump. So sort of just thinking about your scale with the question that you're trying to answer or address. So just a little conclusion of sort of when you're thinking about these tests, what they're trying to answer, what you're trying to do with them. So that BMP is really how much gas can we make? What's the potential of this project? I've seen a fair amount of work comparing BMPs to what people see in digesters. Normally, you're getting 70 to 80% of whatever the BMP number sort of is, right? Because we're not going to digest maybe as completely. We won't have that same feed to microbe ratio. When you saw that work Steve did, he was in between his low and high BMP sort of pretty well, right? So it's a pretty good tool for what he decided you could make, recognizing that one sample doesn't tell you everything about that material, sort of seeing the variation with time was important in helping him set the bounds. And it's really there to answer the question of, is this worth digesting? I wrote a time frame of 30 to 40 days down. I think the digestion, normally a minimum will be about 20 days. And the 30 days would let you get a report written up and sent out and to make sure that you have it all normalized correctly to the characterization. For that anaerobic toxicity assay, you're really asking, is there anything in here that might hurt my digester? Should I be concerned about possible performance issues? And it helps be a first step to think about what's going wrong or some troubleshooting. That test is typically much shorter, right? So I ran it for what, 180 days in the example I showed you, but most people run it for 7 to 10 days and look at just that short term. Is there potential for toxicity or not? And we're asking the question, is it safe to feed? Can I take this thing in at all or not? And then finally, that mini reactor, unfortunately, those take a lot longer, right? So they typically take about 3 to 6 months at a minimum. Normally, we want 3 months of backgrounding data to get through sort of three hydraulic retention times before you start collecting data. So the next 3 months, that 3 to 6 month window is normally when you're getting good data. And you're asking, how will it perform? What are some of the operation things that I might see as challenges? How stable is the gas production? Do I see potential for foaming issues, or do I see VFA accumulation? Or what happens if I slug load something that I normally don't take in, right? So all those tests have useful potential, but they answer sort of different questions about where you are in your project and how you're trying to make it work. I do think mini reactors can be very helpful for troubleshooting some of the things you see, and especially for student training, they're super helpful for helping troubleshoot digesters later because you run into almost all the problems you possibly can run into on a digester at that scale. So the last thing I really wanted to point out is maybe the applied version of those questions or some of the things you might ask. So if it's a new feedstock, we're looking at BMP. Define your ceiling, define how much methane you could make. If you either suspect inhibition or worry this new material might have something in it that microbes don't like, you're looking at an ATA. And I think about that as protecting the biology of the digester. And then mini reactors really are where you're getting at sort of design optimization. And then finally, material handling at the end is really, pilot scale. And you're thinking about how do we actually manage these? What can we tell operators? So there's my contact information. If you have questions, feel free to get them in the chat because we'll try and address them for the next couple minutes. All right, I don't see any new questions. Oh, now they're coming up. All right, so the question is, what is your thoughts about anaerobic digestion in temperatures other than optimal ones? At lower temperatures, for example, more adapted to cold regimes? And that's a great question. To me, it's really about how fast you're hoping the reaction can go. I think covered lagoons are a great example of sort of digesters being effective even at lower temperatures. Um, Certainly, when we get too low, near freezing, it really slows down. But the question there is really about trading maybe the size of the vessel you need for um, how quickly you can get it done, right? So is the heating a cost something I want to deal with? And that's one of the reasons that European BMPs often are 100 days rather than when I say 20 to 30, 20 to 40 days. Oftentimes they're running them at room temperature, so about 25 Celsius, maybe 72 degrees Fahrenheit, compared to when I run a BMP, I tend to be at 90. And there's some reasons to think you should be trying to run the BMP at roughly the temperature you're going to be working with. My experience hasn't been it makes a big difference in how much gas I make. It's been more of a difference in how long it takes it to get done. But there are some substrates, let's say something with lots of oils in it, where the solubility of the oil is dependent on maybe the temperature of the material you're working with, right? So it'll float up to the top and you might get a layer of fat or grease looking stuff. If you're at a low temperature and as I warm up, I maybe can keep it solubilized and worked in, and then the potential can be a little bit different. Uh, so they all work. Anaerobic digestion in temperatures other than optimal ones is just fine. I think it does make you get a larger vessel and you get to start asking questions like, how much more does that cost relative to what I'm going to pay in operating costs of heating it? But you can make them work. Most digesters in the US especially manure digesters, are operated at mesophilic conditions. We do have some more advanced digesters, generally not on agricultural farms, that run temperature phase digestions or high temperature digestion, so above that sort of 100 degrees Fahrenheit range. The reason they're doing that is it might help solubilize or hydrolyze some difficult to digest materials. But there's a price to pay. Those digesters tend to be more finicky. So colder ones tend to be less finicky. Uh, Mesophilic, sort of that 35 C, 100 Fahrenheit range, tend to be maybe more forgiving and easy to operate. And as you get to the higher ones, you can do it. You have to be more attuned to operation. I think co-digestion or monodigestion can work. In some ways, when we say monodigestion, you with manures, it's really already a co-digestion, right? We fed a lot of stuff to the animal and they processed it into one material, but it's not truly one homogeneous material. It has a lot of different things in it. Oftentimes, when we're thinking about co-digestion, you're trying to manipulate some property that we know is going to help our digester be better. So if I have a lot of food waste that I'm taking in, oftentimes that digests really quickly. Thinking about adding it to manure adds buffering capacity to it. So maybe I reduce my chance of souring. Or if I have something that's really liquidy, if I can get some thicker material to add to it, I'm sort of manipulating my volatile solids content to get more gas production per unit volume. So co-digestion typically offers more opportunities to do that, right? With monodigestion, you sort of get what you get and you're just running it through. Co-digestion sort of handles that, and it also tends to build you maybe a little bit more robust microbial communities. Um, I know a lot of people say we really like to run digesters on three substrates, and I think there is something to that, that your community gets more robust. But more robust doesn't mean better. It is more forgiving when you maybe slug load it with something that you don't always take. But if you are super consistent, it's not necessary. But it can, right? The reason you're taking multiple things is there's potential economic value, or we're able to alter that material to sort of give us ratios that we know are better. Thicker solids, but still can be managed in our system, or mixing something with low alkalinity with high alkalinity to avoid souring. So lots of opportunities there. All right, with that, if you have any last questions, happy to take them. Otherwise, greatly appreciate you joining today and look forward to hopefully seeing you in December when Robert Burns will be covering some of those challenges of getting manure out of the barn and what impact that has on digester systems. Otherwise, thanks everyone and have a good rest of your day.